let's take a look of this functional equation with the fixed point technique. So in the previous video, we have used the variation of Cauchy equation to solve this problem. And actually, we can also use the fixed point solution. And actually, in the previous one, we already can see that f of x to be 0 for all x is real number is a solution. It's very clear that. And next, we can also see that f of 1 equals 1 by simply substituting x, y equals to 1, and then x equals 1, y equals f of 1, and then we can come up with this result. So which means that 1 is a fixed point of f. And actually, we can assume if 1 is the only fixed point, and in the original equation, we can just plug in, substitute y to be x. So on the left hand side, we will have f evaluate or at x times f of x equals x times f of x, which means x times f of x are the fixed point of f. Actually, we do not know the range of f of x, x times f of x. However, here we assume assume 1 is the only fixed point, which means that in this case, the range of x times f of x should be 1. Otherwise, other values than 1 will be a fixed point, which conflict with this assumption. So in this case, x times f of x equals 1 for all value of x to be real number. And in this case, f of x will be nothing but 1 over x for all values of x to be real number. So actually, we already come up with all the solution we get in the previous video. The next point is to show that this assumption is correct. So next, in order to prove this assumption is correct, we assume there is another fixed point of f, a, such that a is not 1, which means that f of a equals a. So in this case, in the original equation, we can just plug in x equals 1 over a, y equals a. So on the left hand side, we have f evaluate at 1 over a times f of a equals a times f of 1 over a. So this one will be a because a is a fixed point. So here we have a times 1 over a, which is 1. So we have f of 1, which is 1. And then this one, we have a times f of 1 over a, which means that f of 1 over a equals 1 over a, which means that a and 1 over a are fixed points of f. So in this case, there is at least one fixed point that is larger than 1, which means that if a is larger than 1, then it already okay. If a is smaller than 1, then 1 over a should also be larger than 1. So this claim is clearly correct. And next, we want to show that there is at least 2 fixed points now. So now we assume if a and b are fixed point of f, then a times b is also a fixed point. So now in the original equation, we simply plug in x equals a, y equals b. So that we, on the left side, we have f evaluate at a times f of b equals b times f of a. So as b is a fixed point, this is b. This is a fixed point, this is a. So we have f of ab equals a times b. So we also prove this one. So in this case, suppose a is a fixed point of f, and a is larger than 1, because if there exists another fixed point which is not 1, then we already proved that there should be at least one fixed point that is larger than 1. So in this case, by using this claim, we can let a and b also to be a, which means that a square is also a fixed point. And then if we just use a to be a here we use a to be a, b to be a square, then we can have a cube is also a fixed point. And so on and so forth. Then we can come up with a to the nth power is also a fixed point, which means that f of a to the nth power equals a to the nth power until n tends to infinity, which means that limit n tends to the infinity, f of a to the nth power should also be a to the nth power, limit n to the n power, where a is larger than 1, which means that this argument tends to the infinity, and this one also tends to the infinity. However, for condition 2, we know that f of x, where x tends to infinity, it should be 0, which means that this one is conflict. This one is conflict. There shouldn't be another fixed point than a equals 1. So this is the conflict. This is the conflict. So there should be only one fixed point, which is 1. And so the only two solution to this functional equation is this 2, as we have already calculated in the previous video. And this is the end of this video.